Hello, we have introduced some notation for random variables. We have tried to justify, but we have not formally defined a random variable. Now, let us define a random variable. We say that a random variable is just a real valued function from L to R. That means that you have a set of L, which is your contains all your possible outcomes. L, and consider one member of that. Let's say this C. This one may happen, or this one, or this one. So if this one happens, then you give it to a function. Okay, so your random variable is a function. So input is x. So x input is x, and the output is a real number. So is any function such that the output is a real number. Okay, so this is the first property of a random variable. So on a probability space, so that means that this L here, for this one, you have defined a sigma algebra, and then you have a probability measure. So you know how to measure the probability. So this definition is not complete yet. But such that, so we have these two properties. The third property is that we shall be able to talk about the distribution of a random variable. Now, what is the distribution of the random variable? What is the definition of the distribution of a random variable? It is inside the same definition here. So, which is the probability distribution is the probability of this event. We said that x is smaller than or equal a if this is a real number and this is a function. This is equal to a subset of L, which is all possible outcomes. Okay, all possible outcomes xc inside L, such that x of xc satisfies these a. Okay. So if this is an event, if this is in your sigma algebra, okay, then you can measure these probabilities. So this probability is meaningful. If these probability exists, if this is inside your sigma algebra, then this probability is meaningful, is defined. We call it the CDF, the cumulative distribution function of x. Okay. So everything is self-defined. The CDF is defined inside the definition of a random variable, and it is based on this probability space, because as soon as this is a member of your sigma algebra, this probability is meaningful, and then this has a CDF. We may not have this CDF, so the CDF is associated to random variable via this probability measure that you have defined. So, but these should be defined for all real numbers. So you could have these a, and then you consider this interval. Okay, so so this is, let's say, x and a, and this is your sample space. So this c. And this is your random variable, your machine. So, and then it produces x of c. So this is for this c, let's say it comes here. For this one, it comes here, and so on. So for this a, I consider this subset is going to be a subset of these, and then I measure the probability of these events. I call it the CDF of this random variable. So, so the interval from minus infinity to a, I inverse map it, because what is happening is that I have L, and then the possible outcome of these through this function are mapped here on your set of real numbers. Okay. So let's say this C is mapped here, this one is mapped somewhere else, etc. So for any a, okay, I have to see what are the points in A. So I have to inverse it. I have to inverse this set, the inverse of this function. For instance, this point may have two solutions. This point may have no solution, etc. I put all those solutions together, and this becomes this event. So this this is an abbreviation for the event x smaller than or equal a. Okay, so that means that x smaller than or equal a is the inverse of this interval to this one. So it's a subset of L. And then we want to measure this probability, because this a, okay, if you change this value of a, if you reduce it, then this set here will shrink, will become smaller. So so the value of probability of this event, which is inside your a subset of your sigma algebra, is defined as the CDF. Remember that this is a subset of L, okay, and is exactly equal to this event. And remember that this function is a real function of a single variable. So for different values of a, you could plot the CDF fx of a, and we will see some properties. For instance, we will see that this is a non-decreasing function.